Okay, welcome back. So for most of this semester we have been looking at motion that we could describe using x and y coordinates and z coordinates if we wanted to add 3 dimensions, with the exception of when we looked at uniform circular motion. What we're going to do now is start spending a couple of chapters looking at that rotational motion in a little bit more depth. That brings us to Section 8, Rotational Kinematics. So again, kinematics, the study of different kinds of motion, but without worrying about what causes that motion. After we look at rotational kinematics, we'll start taking a look at rotational dynamics and start looking at why these objects have the motions that they do, what kind of forces are involved, and things like that. So first, we need to figure out how we're going to describe the motion of something that's rotating. Now, this can be any kind of object that's rotating, for example, like a wheel that's rotating, but it could be rotating in any dimension, for example, any object as long as it's rotating. That's what we're doing. We're looking at something that's rotating. So let's imagine we've got some object, and I'm going to draw it like slightly on the side. So here's our object, and there's an axis that goes through it, and this thing is rotating about this axis. So imagine, for example, our wheel here. So here's our wheel, and let's imagine it's rotating. We've got an axis through the object, and the object rotates about that axis. We're going to call this the axis of rotation. Okay? Now, let's imagine that there is a point on the object, and this point is fixed on the object. So as the object rotates around, that point rotates around with it. We might imagine that, say, on our wheel here, there's just a little point on the wheel, and as the wheel rotates around, that point rotates around with it. Now, let's take a look at this kind of from above, in other words, looking down along the axis of rotation. So here's our object, whatever it is. There's a point on it. Here is where the axis of rotation is. So our axis of rotation is perpendicular here, and this is rotating around that way. So now we've got something that kind of looks like this. Here's our axis of rotation coming out of the board. The point here is rotating around on the object. Now let's define, actually I'm going to turn this up a little bit. There's our point. Let's define another axis from the axis of rotation out to the side. We might think of this like the x-axis or something like that. So here's our x-axis. Now the x-axis is stationary in space. As our object rotates around, the x-axis stays still. It's not moving. And this point here is our reference point. Now through the reference point, from the axis of rotation, I'm going to draw another line like that. Now this line we'll refer to as the reference line. And as the object rotates around, that reference line is also rotating around. We're going to use that reference line to define the orientation of our object. So we're going to define whatever this angle is between the reference line and the x-axis. We're going to call that theta. And we're going to call theta the angular position. This is the angular position of the reference line. So notice, as the object rotates around, as this reference line rotates around, theta is going to change. Theta could increase, it could decrease. If the object is rotating, say, counterclockwise, theta would increase. If it rotates clockwise, theta would decrease. Theta would be positive. We'll define theta as positive if the angle, say, is counterclockwise of the x-axis. Theta could be a negative quantity if the reference line is clockwise from the x-axis. Theta could be any angle that we want. Positive, negative, could be 0 if it was right on the x-axis. Now, theta we're going to measure not in degrees, but we're going to measure it in a different, with a different unit. So the units of theta will be radians. Now, I mentioned before that we are going to use radians at some point. Well, this is the point. We're going to use theta to measure the angle of, we're going to use radians to measure the angle of theta, but at no time are we ever going to take trigonometric functions of radians. So don't change your calculator from degrees to radians mode. Leave it in degrees mode, because at no time are we ever going to take sine or cosine or anything like that of this angular position. Okay, now how is a radian defined? What is a radian? Well, typically we usually think of a circle as being divided into 360 degrees. Well, that 360, that is a completely arbitrary number. It was first used because it was very close to the number of days in a year. It's very close to 365. It's also a multiple of a large number of numbers, obviously. 1, 2, 3, 4, 5, 6, 8, 10, 12. So it's a nice round number that divides evenly into a whole lot of different parts. But we can actually measure or divide the circle into any quantity that we want. If we divide it into 2 pi parts, then one of those parts is what we call a radian. So one circle we can think of as being divided into 2 pi radians. Well, if that's also equal to 360 degrees, we can get an idea of what 1 radian is. If we divide both sides by 2 pi, 1 radian would be the same as 360 degrees divided by 2 pi, which turns out to be about 57.3 degrees. So we can get an idea of exactly what this angle is, or at least approximately what this angle is. We take a protractor here. So 10, 20, 30, 40, 50, about 57 right there. So there we go. That is about 1 radian, about 57.3 degrees. Doesn't look like anything particularly special. It's not a right angle. It's not half of a right angle. Nothing like that. But it does turn out to be a very, very useful quantity when measuring angles, as we'll see later. It kind of makes things a little bit easier. All right, so back to our object that is rotating. So here's our object, and there goes my pen cap. So here's our object rotating with some angle theta. Theta is going to change in general. Theta will be a function of time. If the object is rotating one way or the other, theta will change with time. Let's imagine that at some initial time, whatever our t equals 0 time is, whenever we start our clock, we'll assume that our initial angle is theta naught. So theta naught will be our initial angular position. And then at some later time, our final time or whatever, then theta will be our final angular position. Okay? Now, let's imagine that our object starts off at some initial angular position, theta naught, At some later time, some final time, the object has then rotated and our reference line is at some new angle, and that is our new angle. We'll call that theta. A very important quantity that we will see is how much of an angle has the object rotated. So imagine we start at some initial orientation, say here, sometime later we've moved here. How much of an angle has the object rotated through? Through what angle has it moved? Well, we'll define the change in the angular position as the final angle minus the initial angle. So this is a kind of quantity that we've looked at very, very often. The change in something is the final value minus the initial value, and we typically write that as delta theta. Delta, whatever the quantity is, final minus initial. And this is what we will refer to as the angular displacement. Now this is particularly useful. You can just imagine, let's go back and let's draw this over again. So here's our object, and here's our x-axis, here's our reference point, and let's imagine that this thing rotates and is now, say, maybe over here or something like that. Our reference point is up here, and here's our initial angle, theta naught. Here is our final angle, theta. And theta minus theta naught then is this angle between these two. So here is delta theta. Now, it's interesting to notice what would happen if we had chosen a different reference point. Maybe initially we had used a reference point over here. Then our initial angle theta would be, theta naught would be that angle. And then when it rotated around, our new position would be, let's say, here. There's our new reference point, and this would be, the theta would be here. But theta minus theta naught would still be that angle right there, delta theta, and that delta theta would still be exactly the same as the delta theta that we had over here. In other words, while theta and theta naught depend on the reference point you have chosen, delta theta does not depend on the reference point. In other words, back here, if we have our reference point here and the object rotates, the angle through which it rotates by measuring the motion of this reference point would be exactly the same angle as if we had some other reference point, maybe a reference point over here, and it moved through the same angle. The angle through which the object moves is the same regardless of what reference point we chose. So, delta theta is going to be a very useful quantity because it is independent of the reference point, while both theta naught and theta do depend on the reference point. Okay, so we've got the angular displacement of our object. Angular position, initial and final, and then the angular displacement. How rapidly is this thing rotating? Are we talking about something that moves through an angle maybe very, very slowly, or something that moves through an angle much more rapidly? Well, we'll define a new quantity that will describe that. What we're going to define is the average angular velocity. So just like we defined the average velocity when we were talking about linear motion, we can define the average angular velocity when we're talking about angular motion. The average linear velocity that we defined before, we defined as delta x over delta t, the displacement over the time interval. In other words, how long did the motion take? Well, we're going to do the same sort of thing here. We're going to define this as the angular displacement over the time interval, delta theta over delta t. Now typically angular quantities are usually represented, most of them are represented with Greek letters, and for average angular velocity we're going to use the Greek letter, a lowercase omega. So this is going to be a lowercase Greek letter omega. Capital omega looks something like that. This is a lowercase Greek letter omega. It looks kind of like a round W, but it's not W. Don't call it W. It's omega. This is the average angular velocity, so I'm going to stick in a little subscript AV to remind us that that is the average value. Now, what are the units of omega? Well, they're going to be the units of theta. What are those? Well, radians. Units of delta t, seconds. So the units of omega will be radians per second. So let's stick some numbers in here. Oh, let's imagine we've got something, maybe a wheel or something like that. Let's imagine it is rotating. And let's imagine that it rotates through, let's say, 2 complete revolutions. One revolution means one complete circle. So it's going all the way around in a complete rotation, all the way around one more. So 2 revolutions. And let's imagine that that takes, let's say, 3 seconds. Let's figure out what the average angular velocity is. So omega average, that is delta theta over delta t. Well, for 2 complete revolutions, what's delta theta? 1 complete revolution, 1 complete circle would be 2 pi radians. 2 complete revolutions would be 2 times 2 pi, or 4 pi radians. Now, if we want to emphasize this is actually 3 sig figs, we'll write this as 4.00 pi, sorry, 4.00 pi radians, divided by delta t, which is 3 seconds. So take 4 times pi divided by 3, and what do we get? We get 4.19, and then what are the units? Radians per second. So radians per second. Now, exactly like we did from average velocity to instantaneous velocity, we will define the instantaneous angular velocity without the subscript AV by imagining that we're going to look at the average value, but over a very, very small time interval. So imagine that we look at a very, very small rotation. We're going to define this basically using a limiting idea over a very small time interval, so small that let's imagine that the time interval goes to 0 of the average value. In other words, the limit that delta t goes to 0 of delta theta over delta t. So it's the same kind of trick that we used for instantaneous velocity. We've already used that idea in application when we looked at the centripetal acceleration for uniformly accelerated, for uniform circular motion. So it's the same idea. We're not going to actually use this, we're not going to stick any numbers in there, but just conceptually the idea is exactly the same. Okay, so what omega tells us is how rapidly it's spinning. Do we have a small value for omega, or do we have a much larger value for omega? Now, likewise, you might imagine, well, what if it's going slowly and then speeding up? What if it's getting faster? Or what if it's getting slower? What if omega is changing? Well, you might guess we will also have an angular acceleration. We have angular position, angular velocity. We also have angular acceleration. So we will define the angular acceleration in the same way that we did with linear motion. We'll define the angular acceleration first with an average, the average angular acceleration. And we'll define that by the change in the angular velocity divided by the change in time, delta omega over delta t. And again, we're going to use a Greek letter to represent angular acceleration. We're going to use a lowercase Greek letter alpha. So this is a lowercase Greek letter alpha. Capital alpha just looks like a capital A. And again, to emphasize, this is an average value subscript AV. So alpha sub AV. And again, exactly the same way, we'll define the instantaneous angular acceleration in terms of a limiting idea over a small time interval, delta t goes to 0 of, alpha average. In other words, the limit as delta t goes to 0 of delta omega over delta t. Okay, so again, let's stick some numbers in here.